Well, good day, everyone, and welcome to this third session of the seventh lecture workshop on transdisciplinary areas of research and teaching by Shanti Bhatnagar Awardees. Today, we have with us Professor Atish Dabholkar, who's a Shanti Bhatnagar Awardee in Physical Science in the year 2006 and is currently the director of the Abdus Salam International Center for Theoretical Physics, that is the ICTP, Italy. And he'll be talking to us today on the topic quantum black holes, where Hawking meets Ramanujan. He's a well-known figure in theoretical physics, and he became the ICTP fifth director in November 2019. And he's well-known for his research on string theory and quantum black holes, including investigations that build on ICTP founder Abdus Salam's Nobel-winning work on electroweak unification. Born in 1963 in India, he's a graduate of the Indian Institute of Technology, Kanpur, one of India's premier educational institute. He earned a PhD degree in theoretical physics from Princeton University, followed by postdoctoral and research positions at Rutgers University, Harvard, and California Institute of Technology. Until 2010, he was a professor of theoretical physics at the Tata Institute of Fundamental Research, Mumbai, and has been a visiting professor at Stanford University and a visiting scientist at CERN. At ICTP, he was the head of the High Energy Cosmology and Astroparticle Physics section, and he has received many honors, including the Shanti Bhatnagar Award in 2006, which is the most prestigious National Science Prize awarded by the Indian Prime Minister for his astounding contribution for establishing how quantum theory modifies the entropy of black holes and his pioneering studies of supersymmetric solitons in string theory. He is an elected member of the Indian Academy of Sciences, and in 2007, he received the Chair of Excellence Award from the National Research Agency in France. With these words, I now invite Professor Atish to kindly share his screen to deliver his talk.
Okay, thank you very much, Professor Saxena. It's a pleasure to be here, even if remotely. And as I understood, just a second.
Professor
Can you
Atish,
see it all now? Can you see it all?
I can. Yes, you are muted. Yes. Can you unmute yourself? Yeah, can you hear me?
Okay.
Yes.
Okay, so it's a pleasure to be here. It's been a while since I've been to New Delhi, actually. Last time I visited Delhi University was some time ago. And as I understand, I think it's a very nice initiative to bring the latest developments to the young students from the university and also from other colleges, as I understand. So what I want to talk to you about is some very exciting recent work on quantum black holes. And this is where somehow the physics of Hawking and the mathematics of Ramanujan comes together in a very unexpected and interesting way. So that's going to be. Now, I was told that most of you are undergraduates in physics, so I want to use some very basic concepts without really using a lot of equations in a manner that you can get the flavor of what is being done. So you must have learned a bit about relativity in your undergraduate studies. And the essential point of relativity is why it is called relativity is because it's relativity of time. See, in Newtonian physics, the time measured by a person on a train is the same as the time measured by a person on a platform. It doesn't matter whether you're moving or you're not moving. However, it was becoming clear that the speed of light is the same when it is measured, whether it's on a platform or in a moving train. Now, this is very counterintuitive, because if you throw a ball, or if you just hold a ball in a train it would be at rest. But for a person on the platform, it would look to you that it's moving at the speed of the train. So the speed of any material object seems to depend on whether you're viewing it in the train or in a moving or in a platform. But not so for light. I mean, for some reason, light is a very bizarre property, that the speed of light as measured on the train as on the platform is exactly the same, 300,000 kilometers per second. And this can be possible only if the time measured by the person on the train and the person on the platform runs a bit differently. And the one-liner is that the moving clocks run a bit slower. And this also implies that the speed of light is an ultimate speed limit. And this very simple fact, I mean, simple in hindsight, has two very dramatic implications. One is that it implies gravity waves, and the second is that it implies black holes. So that's what I want to tell you about. So this is a nice video made by, I think, Brian Greene. So here is a moving clock. And it basically follows from the Pythagoras theorem that as far as the person on the platform is concerned, the light has to travel longer distance because it has to travel along the on the hypotenuse of this triangle. So if you make a clock in which it is just, when a light bounces once, you call that 1 unit of time. Then it's clear that if that is your definition of time, then if that clock is moving, it looks to you that it has to cover a lot longer distance, and as a result, the time runs a bit slower on the train. Now, this has a dramatic implication, and this is what actually bothered Einstein, because this is directly in contradiction with the Newton's law of gravitation. Because if you remember your Newton's law of gravitation, it says that force between, let's say, the sun and the earth is proportional to the mass of the sun times mass of the earth divided by the distance square times the Newton's constant. There is no time in this equation. So therefore, according to Newton, if the sun disappeared suddenly, if the mass went to zero for some reason, people on earth will come to know about it instantaneously. This is called action at a distance. So according to Newton, the force of gravity acts instantaneously. But Einstein would say, since nothing can travel faster than light, gravity should also, any physical influence must travel at most at the speed of light. And therefore, we will come to know when the sun disappears only 8 minutes later. So this is what led Einstein to formulate his general theory of relativity. And general theory of relativity means it's the general relativity of time, that not only when you are in motion, in uniform motion, but also if you have accelerated frames, you want to make sure that the physics does not change on which frame you are in. And that very simple idea led to this very big revolution in our understanding of gravity. And now we understand that, in fact, gravitational influence does travel at the speed of light, and we will come to that in a moment. The second very important consequence of this ultimate speed limit is that black holes. Because as you know, if you remember your basic undergraduate or high school physics, there is something called the escape velocity. So if you throw a ball, it will fall a bit further at some distance. If you throw it faster, it will fall a bit further. If you keep on throwing it faster and faster and faster, eventually it will start going in this orbit around the, and that's how the satellites are launched in a way. And if you throw it even faster than that, then it will just escape. That's called the escape velocity. Or you can just shoot it up at a speed much larger than the escape velocity. And that will escape the gravitational field of Earth. But now, suppose we make Earth heavier and heavier and heavier, then since the escape velocity is basically obtained by demanding that you can say, if you remember, it's Gm divided by R is equal to V square upon R. So V square. So basically, you're saying that the kinetic energy is equal to the potential energy. That's the escape velocity. And if you increase the mass of the object, the escape velocity increases as the square root of the mass. So eventually, if you keep on increasing the mass of the Earth, it should happen that at some point, even light cannot escape. And this is a very bizarre conclusion, and that's what is called a black hole. That if this fundamental notion of the relativity of time is correct, and if the speed of light is really the upper limit, then even light will not be able to escape if you have to take a sufficiently dense object, sufficiently dense star. And roughly, I think if you compress, alternatively, you could compress this star into a very small radius. If you compress the mass of the sun into about 3 kilometer radius, so you can imagine how dense is that object. At that point, it will become a black hole. And this is an artist's impression of a black hole. It's called black because there is a surface there in the middle where you thought there was the sun at 3 kilometers in the case of the sun, where once you cross that surface, it's like a one-way surface. You can only go inside, you cannot come outside. It's as if you could only come to my talk, but you could not leave my talk. It would be. So it's a one-way surface, and you can fall in, but you cannot come out. And in fact, once you fall in, you'll meet a singularity in the future, and you sort of will be pulled. You'll have a very unpleasant death. But the singularity is in the future. It's not like the singularity is over there. You might have thought singularity is where at the center of the sun. It's not at the center of the sun, but sometime in the future. So this is some peculiar property of general theory of relativity. And a more precise way of understanding this is to see that the event horizon is a stationary surface. It's like a wall which is at a fixed distance. But at the same time, it is moving at the speed of light. It is stationary null surface. This is something that we cannot really imagine in normal geometry. But the geometry of space-time around the black hole is so weird that this 3 kilometer point is at the same time traveling at the speed of light. It's sort of coming out. And therefore, once you cross it, since you cannot exceed the speed of light, you cannot come out of it. You can only fall inside. So, and in fact, this led Chandrasekhar, as you know, once a star slightly bigger than our sun runs out of the nuclear fuel. So why doesn't the sun collapse actually into a black hole? Because as you know, there are a lot of atomic explosions are happening, hydrogen fusion is happening. And there is a big, very hot gas, and the pressure of that gas is counterbalancing the force of gravity. But once you run out of the fuel, there is no way you can heat the star. Then nothing can really stop gravity, because gravity is inexorable force will just pull everything inside, and you won't be able to stop the star from collapsing. And such a star will gravitationally collapse to form a black hole. And this conclusion was so bizarre that leading physicists, including Einstein, in fact, Einstein wrote a round paper. So you should really study this a bit about the history of science. It's not always that when you read it in a textbook, it all looks simple and straightforward. But some of these ideas, encountered very serious intellectual difficulties and very serious intellectual opposition from leading scientists like Einstein and others, to the extent that Chandrasekhar, in fact, left the United Kingdom to go to the US, partly because Eddington was really against this idea. And Eddington was a leading astronomer in UK at the time. But it turns out that Chandrasekhar was actually right. And in fact, Einstein was also right. I mean, he was right about the gravity waves. He was wrong about the non-existence of black holes. And this was one of the most beautiful experiments done, for which I think in 2016 there was a Nobel Prize awarded. So this is a merger of two black holes happening a billion light years away from us, and which was detected in 2016 in this laser interferometer. So what happens is that this produces, when the two black holes merge, they lose, some of the mass gets converted. The mass of the final black hole is smaller than the sum of the masses of the two black holes. And as a result, that enormous energy, since E is equal to mc square, which is actually more energy than all the energy of all the stars for that particular flash of time in all of the universe, and that is released, but in the gravitational waveform. So you cannot really see it. It's not light. It will not go through your eyes. And here you will see just a small perturbation, little wiggle in our space-time when the gravitational wave passes through. And that's what people measured using this very delicate and beautiful experiment, which is called the LIGO experiment. And as you know, India is now trying to be part of this. It's called an INDIGO. Hopefully soon, there will be an INDIGO laser interferometer installed in India, which will increase the possibilities for gravitational wave observations. So now, maybe I can pause and ask, maybe I can take, do you think it's a good way to stop and ask questions at this point, or should I just continue?
Yeah, there's one question. One is whether these quantum black holes are simulated objects or experimental findings, but you already have answered that part.
Yeah, so I will come to that in a moment. So far, what we have been talking are classical black holes, because I never talked about Planck's constant, h bar, in this. I talked about the speed of light, but I didn't talk about the Planck's constant. The second revolution of the 20th century physics was attributed to the discovery that there is something called the Planck's constant, and there is a least action principle. There is an action cannot be smaller than h bar, or the uncertainty between a position momentum cannot be less than h bar. So that h bar, just like speed of light was an ultimate speed limit, h bar placed some kind of an ultimate action limit. You cannot go lower than h bar. And that's where my subject of my talk enters into picture, that I will be talking about quantum black holes and not just classical black holes. So why do we need to talk about classical black holes? And I will address this question that was raised. So relativity describes nature at very long distances, all the way from the solar system to the universe itself, with all kinds of exotic objects like black holes and pulsars and so on. And it generalizes, as I said, Newton's law of gravitation. It predicts gravity waves and black holes. But this is only one part of our story, because I have to now describe to you the quantum part of the story. And as you know, quantum theory describes nature at very short distances. This has been enormously successful in describing atoms, molecules, and the physics of the atomic nucleus. And this underlines much of the modern technology, even this talk that is happening. We really need semiconductor technology and lasers, and all this really depends on understanding the quantum world. In particular, one of the major discoveries attributed to Dirac, for which Dirac got the Nobel Prize at a very young age, is that it predicts an antiparticle for every particle. If you put relativity and quantum mechanics together, you have this inevitable conclusion, really without going into too much mathematics. It just follows from causality, that every particle must have its antiparticle. In particular, electron antiparticle means it has the same identical, exactly the same mass, but opposite charge, whatever charge it might have. So Dirac predicted, just based on pure thought, that the electron should have a positron. And actually, he was not believed for several years. 3-4 years, he was not believed. And then suddenly, Carl Anderson discovered this on his photographic plates. Because you put some magnetic field and you find some cosmic rays going in the wrong direction. because electrons you expect to go in a certain direction if you have a magnetic field, just because the magnetic field bends charged particles. They found evidence for things going in the opposite direction with the same tracks as electrons, but going in the opposite direction. So this was actually a monumental discovery. And despite the enormous success of both these theories, as I told you, general relativity has been enormously successful. Quantum mechanics has been even more successful, you would say. It really has come to pervade all our life with our mobile phones and everything. It really depends on quantum theory. So somebody has joked that 1/3 of the American economy depends on the Planck's constant. But when you try to put these two theories together, you run into some very violent contradiction, some really serious theoretical problems. In particular, you have a sun going around the Earth, Earth going around the sun. So you might say, okay, but this system is also quantum mechanical. You have to treat everything quantum mechanically. So if you treat the Earth and the sun in a quantum mechanical way, roughly speaking, I'm simplifying a little bit, what you find is that the force of gravity, instead of the quantum correction to the force of gravity, instead of being small correction, which is what you would expect if it was really a correction, it is infinite. And this is, of course, in contradiction with what we observe. I mean, if the force of gravity was infinite, then we wouldn't be here talking about it. So theoretically, it's a very challenging and very important problem to find a theory which combines both these theories in a single framework in a manner that is mutually self-consistent. And these two cornerstones of modern physics both work very well, but they are mutually inconsistent. And the challenge, which has been occupying me and many other physicists around the world, is to find a consistent framework that unifies the two. This is therefore goes in the same vein as the idea of unification of all forces, for which Abdus Salam got the Nobel Prize, to unify the weak interactions with the electromagnetic interactions. But you should also unify, maybe, you certainly need to unify other forces, but more importantly, you need to make it, even if you don't believe in unification, you have to have a formalism in which quantum corrections to gravitational phenomena are calculable and small. Otherwise, all the success of Einstein's general theory of relativity would not be valid anymore. And so that's clearly a very important open problem. And that's the reason why we study black holes. That's why I'm studying black holes, because black holes is one place. See, physicists have to look for place where, you want to combine quantum mechanics with gravity. Now, when you're looking at a semiconductor, the force of gravity is so weak that you can just forget about it. If you're looking at a huge black hole, then the quantum effects are so small that you can just forget about it. But if you look near a black hole, then quantum effects are sufficiently interesting and important, and they have rather bizarre consequences. So black holes are really bizarre in every possible way, but in a manner that is really based on very solid understanding of our laws of nature. So it is not, they're bizarre, sort of go against your intuition, but there are very serious, important theorems which show that singularity must exist, event horizon must exist. And Hawking's result is even more theoretical, but it's based on very solid physics, based on general relativity, quantum mechanics, and thermodynamics. And what Hawking found was that, surprisingly, black hole is actually not black, but it is a little bit like a hot piece of metal at some temperature. So this is a very remarkable connection between relativity, quantum theory, and thermodynamics. And just like a hot piece of metal will be radiating, heat waves, or if it's red, some red light, and so on, given by some Planck distribution, Hawking found that actually the black hole emits rather like a metal, given by a Planck distribution, radiation of various kind coming out of the black hole. And the physics of it is very simple. The mathematics is a little bit complicated, but I will try to explain the main physical idea. If you accept that there is an event horizon where things can fall and it cannot come out, and then if you accept that in quantum mechanics, there is always uncertainty. Just like there is a delta X, delta P uncertainty, you can have some uncertainty in energy so for a very short time. So delta E, delta T also has to be greater than h bar. And one way to think about that is that even when we're talking here, the room is full of, constantly it is popping out these virtual pairs of electrons, positrons, protons, antiprotons, and they're getting annihilated. But that's happening so quickly, like in 10 to the minus 15 or even shorter time scales, that we don't even notice them. I mean, what we see is somehow after that effect has been subtracted out, because our senses are not subtle enough to notice this. And now what can happen is that near the horizon, one of the things on the pair, like this one, the green one, it can fall inside and the red one can escape to infinity. And it would look to you like the black hole is radiating. Now that raises a very, so this Hawking solved a very interesting, I mean, he showed a very interesting and amazing connection between thermodynamics and quantum mechanics and relativity. But that raised another puzzle, because as you know, in quantum theory or in atomic theory, we understand something which is hot, like let's say the air in this room is hot because the molecules are moving around, kicking around, and they kick you once in a while. And if you raise the temperature, they start moving faster and faster, and then you feel hot because their kinetic energy increases, average kinetic energy increases. So basically, you can always explain in statistical mechanics, this is called statistical mechanics, the thermodynamic properties can always be explained by some statistical behavior, that on average, if you increase the temperature, basically temperature is nothing but the average kinetic energy of the fundamental constituents of matter. And this observation was really fundamental. You may have studied the Maxwell-Boltzmann distribution, and in a course, it looks like some small simple fact. But this was really one of the gigantic important steps in physics. And that's why Boltzmann got his name attached to it, the Boltzmann entropy. Boltzmann really, this is a very, very profound insight. That by studying thermodynamic properties of, let's say, the gas in this room, you could predict that it's actually made up of atoms, even at a time when you couldn't actually really look at atoms. Because if I ask you, why do you believe in atoms? Right? We cannot really see them. Nowadays, maybe we can see them under some electron microscope or something like that. But in the 1860, at the time of Maxwell and Boltzmann, how could you conclude that the air in this room is made up of molecules? And it was a model. You say that, okay, it's made up of little particles, and you calculated the temperature properties, thermodynamic properties from this as some statistical averages. And very surprisingly, you get the right agreement. And there is a very fundamental quantity, which is called the entropy, as you know, which is what allows us to make this connection between the macroscopic physics, or the physics at large distances, at the human scale, and physics at the microscopic scale, at the atomic scale. Okay, so Hawking's discovery raised another problem that, okay, we understand why a metal is hot, but can we understand why a black hole is hot? What are the atoms that make up a hole in space-time? Black hole is literally a hole in space-time. So it really, you're asking a very fundamental question about the quantum structure of space-time. And the answer to this question leads us to string theory and ultimately to Ramanujan, which is what I want to explain. Okay, are there any questions at this point?
Yeah, there are two questions. The
Okay.
first one is, what does it mean that energy is released in the form of gravitational waves? In one of your slides, you mentioned that part.
Yes. So it's very much like if you have a dipole, let's say in electromagnetism, right? If you have some atom which is oscillating, a dipole, then you get electromagnetic waves, right? So you have probably studied this. You can calculate the Poynting vector. Basically, there is a radiation field is produced. There is an electric field which is oscillating this way, and the magnetic field which is oscillating at a perpendicular direction, and the wave is propagating in this direction. This is how we do an antenna, right? The radio antenna is basically you kick around the electrons in the antenna, and they produce an oscillating electric field and oscillating magnetic field. And that, if you calculate the cross product E cross B, that's the Poynting interval, tells you that energy is actually being propagated in that direction. That's more or less how you can do it in Einstein's general theory of relativity. There is a kind of a gravi-electric field and a gravi-magnetic field. So Newton's law, which depended only on static distance between the two, has to be modified. And you actually end up introducing, just like in electromagnetic theory, you don't just have a potential, but you have electric field, 3 of them, and 3 magnetic fields. There's a similar story when it comes to graviton, or gravity waves. And basically it's an oscillation of the metric field, which you can think of as an oscillation of space-time itself, that how do you measure the distances? And that you can show carries energy, very much like how electromagnetic waves carry energy. Okay.
Okay.
The next.
Yeah, there is one more question. Why the merger of black holes release only gravitational waves? And is there something else which is also released?
Yeah, so I think there are some very interesting events involving neutron stars. See, because if you have a neutral star, then it has no electromagnetic field. But imagine you had a neutron star, then you have a magnetic field. And now, as I said, it's a oscillating dipole, if you like. If you have a neutron star going around, then it's like it has dipole moment. And again, you can calculate the radiation of electromagnetic waves. So these are called, these events are very interesting because you can observe these events. These are called messenger events. You can observe them both as a gravitational waves and as an electromagnetic wave. They might produce some electromagnetic waves which you can detect in electromagnetic telescopes. At the same time, because the mass, which has nothing to do with charge, is getting, basically it has related to the fact that when you have a rotating, suppose you have 2 charges rotating around each other, plus and minus. This has a time-dependent dipole moment. And time-dependent dipole moment leads to electromagnetic waves. If you have 2 objects going around each other, it has time-dependent dipole moment, but also it has time-dependent quadrupole moment. And it turns out that for a graviton, which has spin 2, for some technical reasons, it actually emits because of quadrupole, time-dependent quadrupole of the system. So you're right that you can also have electromagnetic radiation at the same time. Depends on the system. If it is charged or if it has magnetic field, then it can. Usually, you don't find charged objects in the astrophysical situation, but you do find large magnetic fields. The neutron star has large magnetic field, and so they can emit large electromagnetic radiation. Okay.
Yeah. Thanks. Please go ahead. Yeah.
Now let's continue with this very important concept called entropy, which I'm sure you have studied in your undergraduate physics, but it's really one of the more subtle and profound concepts in physics. And I can give 3 lectures on entropy. And it has all kinds of different aspects to it. For example, the simplest reason why entropy's concept was found by, people like Carnot and Clausius. They were trying to design efficient steam engines, heat engines. What is the most efficient steam engine you can make? And then you come into this question, why does heat always flow from a hot body to a cold body and not the other way around? How can you quantify this irreversibility? And that allows you to, these deliberations led to this very important concept called entropy. So if you, let's say, you put a heater in this room, you can measure by looking at the electricity bill, how much heat is added to this room. And you are at room temperature. So you say that if you add this heat slowly, then the change in entropy is the slow change in the heat that you have added divided by the temperature. Okay. And then you have the famous second law of thermodynamics, which says that in an irreversible process, net entropy always increases. And the best you can do is to have an irreversible process where the entropy doesn't change, but otherwise entropy will always increase. Now, compared to heat, which is not an intrinsic property, you see, heat is not something intrinsic to the object. But entropy is something intrinsic to the object. You can really talk about the entropy of this gas in this room. And all hot bodies have entropy. And therefore, black hole also must have entropy. How does that help us to understand irreversibility? That's from the second law of thermodynamics. Now you can explain all kinds of irreversibilities in nature that you observe. If delta Q flows from a body at temperature T1 to a body at temperature T2, then the net change in the entropy will be delta Q absolute value divided by 1 upon T2, because that is what is gained by the body at lower temperature, and minus delta Q divided by T1. That is what is lost by the body at a higher temperature. And if delta S is greater than 0, T1 has to be bigger than T2. So the second law of thermodynamics, which people sort of arrived at by hit and miss kind of reasoning, allowed them to formulate in a more precise way what is the most efficient steam engine, and what happens. The most efficient steam engine is when you can have some reversible steam engine, like the Carnot cycle. If you have an irreversible cycle, then it will be less efficient. But you cannot really go more efficient than a Carnot cycle because of the fact that entropy always increases. At best, it can be 0. It can never become negative, change in entropy. So that explains some thermodynamic law. I mean, that formulated some thermodynamic law that energy is conserved and entropy always increases. And then came along Boltzmann, who made this really fundamental observation that in fact the entropy is related to the number Pn of different states of the system for a given energy, n. This is a famous Boltzmann relation, and putting Boltzmann constant k to be 1, so that just a unit, then Boltzmann entropy is log of Pn. So it's basically the number of ways in which you can partition the energy. So for example, in the room, if you have millions of particles going around, you can have a particle going that way and a particle going that way. It will have the same energy as the particle going up and particle going down. So there are really billions of possibilities which will all have the same energy. And this is a relatively simple calculation you can do. It's a counting problem, which is what you do in your thermodynamic course. And when you calculate it, you find that, amazingly, that entropy that you calculate by doing this counting problem agrees with this entropy, macroscopic entropy that you measure by doing some experiment, like heat. You heat the room, change in entropy divided by temperature. You see how much has the entropy changed. And then you calculate it using molecules moving at a lower temperature compared to molecules moving at a higher temperature. You calculate the change in entropy, and that agrees precisely with what is observed experimentally. So this gives an important connection between a macroscopic thermodynamic quantity and macroscopic quantity called the number of ways. This explains the irreversibility that we observe in nature, that you can break an egg. If you drop an egg, it will break, but you will never see that somehow, except if you watch some movie that is running backwards. Suddenly the egg assembles itself into a nice egg. This will not happen. If you shake a jigsaw puzzle, it will break. It's much harder. You have to work for many, many hours to assemble a jigsaw puzzle together. That's because the entropy has a tendency to increase. So simply because there are hugely more states when the puzzle is broken, the entropy is much larger. So that's the natural way in which you can go. Now, what about a black hole? What Hawking found was that it has temperature. But in fact, he found that the temperature is precisely proportional to 1 upon the mass of the black hole. So he found a very precise formula, which I will not explain. Now, if you use the first law of thermodynamics, which says that change in energy is the heat added to the system, which is nothing but dE is equal to TdS. So if you know the temperature, which goes as 1 upon m, right? If you have dm is equal to 1 upon m proportional to ds, this implies that ds is equal to dm square. And I told you that there is this event horizon that you find in the black hole, and the radius of that event horizon is proportional to the mass. It's like g times m. This is called the Schwarzschild radius. So we come to the conclusion that the entropy of a black hole is proportional to the square of the mass of the black hole, or in other words, the square of the radius of the black hole, or in other words, the area of the black hole. And in fact, Hawking's calculation allows you to, in fact, precisely calculate this coefficient 4. There are some h bars and c and g which I have suppressed. I'm using the natural units where h bar and c and g are all 1. So now we have a very precise question in front of us, that just like you could explain the entropy of a gas in this room, can we explain the entropy of a black hole? And that's where string theory comes into the picture. Okay, I have another 15 minutes, right? Now, string theory imagines that the fundamental constituents of matter are not point-like, but string-like, moving in some 10 space-time dimensions or 26 space-time dimensions. This sounds like a bizarre idea. Sounds like almost a very trivial generalization of your normal idea of an electron as a point particle going around. But this very simple generalization actually has very deep consequences. And in fact, what you find is that you get a theory where the divergences of quantum gravity are absent. First of all, you get a quantum theory of gravity automatically. And the divergences that you observe are in quantum gravity are absent. Okay. So what's the idea? What do I mean by that? It automatically contains gravity. The idea of a string is that if you have a string like a violin string or a sitar string, different elementary particles correspond to different musical notes produced by this elementary string. I mean, you just do the harmonic expansion, harmonic analysis, and just look at the different harmonic modes. The different modes correspond to different particles. And in particular, one of the modes that you find is in fact the graviton. This was a big surprise actually in string theory early. There was no reason why suddenly by quantizing a string, you should get a gravity. But if you put relativity and string theory together, if you want to create a consistent theory of strings, which is relativistically invariant, you're forced to conclude that one of the particles, one of the excitations of the string is a graviton. So not only do you get a theory of gravity, but it's forced upon you. You really cannot have a theory of strings without having a theory of gravity. This is really spectacular because you don't then have to postulate gravity as some separate force. You just postulate string theory and you get gravity. And moreover, at least in perturbation theory, when you can do this small calculation, quantum corrections that you can calculate, string theory does not lead to infinite answers. String theory leads to finite answers. But now, what about these extra dimensions, 10 dimensions or 26 dimensions? Well, we live in three-dimensional space, height, length, depth, and time. Three-dimensional space and one time, 4 dimensions. Let's call these directions 1, 2, 3, and 0. Now, consistency of string theory requires that you need additional dimensions like 4, 5, 6, 7, 8, 9, or more, depending on what kind of string theory you're considering. So one possibility is that these extra dimensions can be curled up into small compact balls, and we don't see them in our daily life. but we will be able to see them using black holes. So what do I mean by that? I mean, imagine the 0, 1, 2, 3 are going along this axis, okay? And the other internal directions are going along this axis. And imagine that you have compactified these directions. So they are really like a little circles that you don't see because they're so small that you don't see them. Now, if you're like an insect on this wire, it's like looks like a wire. But the insect on the wire, you cannot really go around the wire because the wire is, insect is too big compared to the wire. Insect can only move in this direction. So the insect sees only 3 large spatial directions at one time, even though secretly there is this small circle which is there for the wire. Now, how does this idea help us in understanding the entropy of the black hole, and where does it connect to Ramanujan? This is what I will try to explain in the remaining few minutes. It turns out that a class of black holes can be described in terms of oscillating strings. So you imagine there is a string wrapping here, you know. So for you who is living in these large dimensions, this wrapped string, you will not see the internal structure. You'll just see a point particle, which will look to you like a black hole. But actually, it is a little string. And now, because it's a string, it can oscillate. It can oscillate in all the transverse direction. So you remove the time and the direction along which the string is extended. That leaves you with 8 directions, 8 transverse directions. In certain forms of string theory, you get 26 dimensions. So 26 minus 2 is 24 dimensions. And now the question becomes very simple. You do the harmonic analysis, and there are different modes of the string with different frequencies. If you have a longer harmonic mode, it will have lower energy. And now you ask the question, how many ways can I make the string oscillate? It can oscillate this way, it can oscillate that way, it can oscillate with shorter frequency, with longer frequency, such that the total energy adds up to P of n. So this problem therefore reduces to a problem of computing P of n. Okay? And this is where Ramanujan comes into picture. Ramanujan, as you know, he's really among the great mathematicians of all time. I mean, he's counted in terms of his intrinsic abilities among the all-time greats like Euler and Gauss. And he made profound contributions to number theory. You must have seen this movie called The Man Who Knew Infinity. And his inspired ideas have kept mathematics busy for many decades. And he was interested in precisely this problem, together with Hardy from Cambridge. But he said that, okay, he was interested in this mathematical problem, okay, and I can state this problem very easily. Partition a large integer n, or any integer n, let's say, using 2 different colors. So let's say 3. You can partition it as 1 plus 1 plus 1, all green or all red, or 1 plus 1, 2 green, 1 red, like that. So there are 10 ways of partitioning number 3 using 2 different colors. This problem is exactly identical to the problem that I told you before, that how do you partition the energy n in the different oscillator modes of a string? Because oscillator modes of the string have integer frequencies because the string is closed. So it has integer frequencies. So again, you're identically led to the same problem that Ramanujan was interested in. And here is a little clip from this movie. Can you hear? Sorry.
Yeah. No. If you can play, I think you have to share the sound.
Now I have to share the sound.
Yes.
So
So when there was a share screen option, you have to share it with sound. Then only we can hear it out.
Can you hear?
Yeah, but we are not able to see anything.
Okay, now I'm sharing it. I can see. You're sharing a screen. Maybe I'll stop the video. Okay, can you hear? Can you see?
No, I can see, but we cannot hear.
It's a pity. Okay. Well, I can translate what is being said, okay?
Yeah, please go ahead. Yeah.
So here Ramanujan meets. Okay, so what I can do is I will just stop the audio here. Okay. Okay, can you see?
Yeah.
Okay, so here is a famous mathematician called Hardy, who got Ramanujan. I could hear now.
Yeah, I also could hear it. Maybe you can play it. Yeah. Yeah, I can hear it.
Well, here we are, P of 200, the moment of truth. You know,
No, so I think I went forward here. Okay, this maybe it's not seen, heard, okay? So here, basically Ramanujan, this is Major McMahon. He was a major in the UK, in the United Kingdom. And this is Hardy who takes Ramanujan. And he basically insults Ramanujan, saying that, okay, go back to this Chennai, wherever Madras, where you came from, you couldn't. I mean, he was kind of racist almost. It's not surprising for that time. And he says that you tried to solve the prime number problem and you failed. Now you're trying to solve this partition problem. But I have been working on it for many, many years. And I don't think you have to really do it by hand. And I don't think some random person can solve it, especially not somebody like you, coming from India with the brown skin and so on, right? I mean, it was like, that's the implication. And Ramanujan said, no, I can actually do it and I will show you. Okay, so the next, Ramanujan had a beautiful formula. This is what happens when he returns.
Well, here we are, P of 200, the moment of truth. You know, I was stationed in Madras once. Yeah. Well, you first. What has your formula given you?
3,972,998 million.
My God. You're close. Within 2%. Well, I'll be damned.
Major McMahon, may I introduce you to Mr. Ramanujan?
Okay. So if you look at how did Ramanujan do this? The way Ramanujan was able to do that, he had some very beautiful formula using some modular properties, some symmetries of this function, which told him that this P of n grows exponentially with a very precise coefficient 4 pi times square root of n. where n is much larger than 1, like 200. Suppose n is 200. This is how he got the answer without, whereas McMahon had to do a long calculation, really by hand doing, okay? But this is exactly what we need, because now if we take the logarithm of that, the entropy will be 4 pi square root of n. And then you can ask the question, if string theory really is the theory of quantum gravity, does it agree with the entropy of the black hole? And in many, in fact, very large number of such black holes, one has found that in fact, there is a beautiful agreement between the entropy computed using Ramanujan's formula and that computed using Hawking's formula. So this is where Hawking meets Ramanujan. And so how did Ramanujan do it? Okay, since you are physics students, I can tell you. So Ramanujan said, whenever you have some counting problem, it's a really good idea to construct a partition function. So he said that, let me define a partition function. So there is a mistake here. It should be q to the 4, q to the 6, like that. Okay. He defined q times z of q. Z of q is a partition function as 1 plus q squared to the power 24. And 1 plus q squared plus q to the 4 plus q to the 6, 24 times 1 plus q to the 3 plus q to the 6 plus q to the 9, like that, all the way. Now, your counting problem is reduced to looking at the coefficient. You just expand this function, which you can put it on a computer, and expand this function to the order n, capital N. So you keep all the terms which add up to n. So you can get n coming from q times qn minus 1 or q squared times n minus 2. There are many possibilities. And those possibilities are precisely the possibilities that go into this counting problem. But Ramanujan noticed something very important. See, this is just a geometric series. The geometric series tells you that you can just 1 plus x squared is 1 upon 1 minus x. Sorry, I forgot 24 here. Everywhere there is a 24. And he discovered that this function has a very beautiful symmetry. It's called the modular symmetry. So in very simple words, it's a function which is highly symmetric. So you're used to some functions, like sine. Sine function is periodic, right? That allows you to say something about the sine function, which you cannot do for a generic function. For example, you can do Fourier expansion if it's a periodic function. Similarly, the fact that it is symmetric allows you to actually predict some properties of the coefficients, Fourier coefficients of this function. And this is how Ramanujan, using this modular symmetry, was able to do it. And the modular symmetry in particular tells you, if you're at q is equal to e to the minus 2 pi t, where t you can think of as like some temperature, then z of t is basically z of 1 upon t. Now this, as you can see, is a very non-trivial symmetry. You see, suppose you take a function like f of x. F of x is not the same as f of 1 upon x, right? X is not equal to 1 upon x. Or sine x is not the same as sine of 1 upon x. So this class of functions is very restrictive and highly symmetric. And that allows you to predict these properties that Ramanujan was able to do, using this very beautiful, precise expansion called the Hardy-Ramanujan expansion, giving you not only the leading answer, but in fact the sub-leading answers. And this formula has proved to be very useful recently to study quantum corrections to black hole entropy. So basically, I will stop here. Sorry, this was a talk I also gave in Ljubljana University. So that's why it says Najlepša hvala, which is thank you very much in Slovenian. But I would say shukriya, dhanyavad. The road ahead is now for physicists like me who are interested in quantum gravity, is that the black holes really give you a very powerful tool to really probe the theory of quantum gravity. See, otherwise you can imagine all kinds of things. How do you know whether string theory is the right theory? Because we don't have real direct experiments at the moment to really establish whether string theory is true or not true. However, these kinds of calculations give you an indirect, it's a little bit like what Boltzmann was trying to do. If your entropy calculation does not agree with the entropy of the, let's say, the gas in this room, then you know that your model of atoms is wrong. In the same way, if string theory failed to give this agreement with Bekenstein-Hawking entropy, we would know that string theory definitely cannot be the right theory, because it's way off from giving you the right answer. What is really surprising is that not only does string theory give you the right answer for Hawking's calculation, but even these sub-leading corrections, and in some cases it has been possible to calculate them very precisely. This is how the quantum effects modify the entropy of the black hole. And that also, all these coefficients A and B, they agree really on the nose. And so that's really very remarkable property of string theory, which gives you some confidence that maybe we are actually onto the right theory of quantum gravity. But only time will tell whether string theory really is the theory of quantum gravity.
Thank you very much.
So this is ICTP. This is where I'm the director. It's a very beautiful campus. On the this is ICTP over here, but we are here on the right on the Adriatic Sea. So maybe some of you will visit us sometime in the future. Okay, I will stop here.
Thank you very much, Professor Atish, for enlightening all the students, faculty members, and research scholars who are attended this particular session. And I hope that your words of wisdom, as well as the way you have explained things, must have brought this particular complex topic, which seems to be a very complex topic, in a very simplistic manner, and some of the doubts which must have been clear for the students. It was a rare opportunity for us to have a person of eminence like you to talk to the students in India, and especially during this pandemic when the F2F instruction has come down to a minimal, and now the things are getting back to normal, but still getting an opportunity to listen to you is one of the rare opportunities, I can say. So thank you very much, and on behalf of the host organization, the Dayal Upadhyaya College, University of Delhi, and the National Academy of Sciences India Delhi chapter, I would like to thank you once again, and to all the attendees who have been there with us for this particular session, and hope to see you all again in future in our upcoming lectures and webinars under this 7th lecture workshop. Thank you very much.
Okay. Thank you very much.
Okay,
Bye-bye.
bye-bye. Bye-bye.